Hi, so I'm going to start with Chapter 6 by explaining machine language. So by this point in your life, in your career, you should understand that this machine that's in front of me right now and in front of you if you're watching this on a computer, it's a device that reads data from memory, and some of that data it might interpret as an instruction to execute. So this is kind of the main way that our machine works. It pulls information from memory and executes code, and that code might be writing back out to data. Fundamentally, data and the instructions to manipulate the data, they're both stored in the same place. They're both treated the same way on these computing machines. So since it's some of that data on a computer is stored as a sequence of off-on bits. So some of that data is instructions to the machine, and there is a language where those bits form the alphabet, and the patterns of bits that your CPU has been implemented in the hardware to interpret, those form the language of your machine, the words to your machine. So machine language is a language made up of binary coded instructions. It's built into the hardware of a computer. The question on the slide is, why would anyone choose to use machine language? You don't have a choice. At some level, the machine has to carry out the instructions. And until you write perhaps a program that can translate from some other language into the language of your machine, you've got no choice but using the language that it understands. Later we'll look at things like assemblers and translators that let you write in other languages, but before it gets executed, it is translated to machine code, which is sometimes called object code. So machine language, or an object code, machine code, has certain characteristics. One is every processor has its own set of instructions that it understands. It's built into the CPU with that binary representation of the instruction. Each machine language instruction generally does typically one very low level task. There is a cost for complexity in the CPU. So we try to keep things simple. We try to keep these instructions simple, and we are able to accomplish complicated things using a lot of simple instructions, but our fundamental building blocks are small. In this course, in order to play with machine language, we are not going to use the Intel Ch06 instruction set. That is more complicated. We're going to use a simpler machine called PEP8. It's designed for teaching. It doesn't correspond to a real physical CPU, but to a simulated CPU. It's actually software that runs on your computer. This is for some hypothetical machine, and it has a lot of the important features of a real machine. So by playing with PEP8, you will develop the mental pathways it takes to understand assembly. And should you, for some reason, need to deal with Motorola, I think it's HC11 or an x86 processor or whatever, you will be ready to do it. Okay, so this processor takes 39 special combinations of bits that it interprets as instructions. The PEP8 processor, it has registers, which are very fast storage, easy to read and write for data. So generally your data might be memory, and memory is a huge store of addressable data. It's not stuff that you can operate on directly in the CPU. So usually with the CPU, you'll pull from memory into a register, do something, and write it back out to memory. And dealing with memory is sometimes a little bit slower or has some kind of a cost. The efficient data is implemented in the digital logic as a register. Registers that we have here are the program counter, and that register is the next instruction that will be fetched and interpreted by your CPU, executed by your CPU. The instruction register contains a copy of the instruction that that was just executed or that's being executed. And the one piece of data that we're going to be working on as a register is the accumulator or A register. Now PEP8 has other registers, but we're not going to be dealing with them right now. In addition to that register, we have 64K or 2 to the 16th. That's the complete address space if you have 2 bytes of memory that we can read and write. That's storage. The architecture of PEP8 looks a little bit like this. Each square is a bit. We have a register, that's the accumulator. We have a program counter. Generally, the program counter is the next thing that we're going to read. It keeps incrementing to the next instruction. So each instruction is 3 bytes long. One is sort of an operation specifier, and the other is an operand, so data that the instruction operates on. Each one is 3 bytes long, so generally the program counter keeps incrementing by 3 as you move through a program. There are a few program special instructions that cause that program counter to jump to different parts of your code. The memory is indicated here in orange, is a great big array of bytes. So 8 bits has a name, 0, 1, 2. So you give me a number, and I will go out and I will find the byte that corresponds to that address or that number. So 0 is the first one, and 2 is the third or byte of data that your computer has. The instruction format goes like this. The first 8 bits are an instruction specifier. These really contain the semantics of what you want to do. The second word, or 16 bits, is an operand. Now this operand is either a number to do something with or a letter. It could also be the address that you want to go and fetch something from. Right? The instruction specifier can be broken up into parts, and depending on the instruction, it's broken up differently. For many instructions, the first 4 bits give you some sort of a semantic opcode of what you want to do. Load something into a register, or write a register into memory somewhere, for instance. Generally, if you're going to load something, these 4 bits would be saying you're going to load something, and then this bit would be 0 if you're going to load it into register A, and 1 if you're going to load it into some other register. Your last 3 bits are the address mode, and they tell you how to interpret the operand. So the operation code specifies which instruction to carry out. The register specifier, if this opcode corresponds to something that can manipulate a register, will tell you what register you're going to be using. And then the address mode specifier says how to interpret the operand. There are 2 address modes that we're going to start off using. There are other address modes, but we're not going to deal with them yet. The first is specified by a pattern of all zeros, and that means we're using immediate mode addressing. That means that the data we need to operate on is stored directly here in the operand. So if we're going to add something to register A, the thing that we would add is what's stored here in the operand. The other address mode is called direct addressing mode, and what that means is that the operand gives you the address in memory of the data that we're going to be dealing with. So here, if we were going to be adding something to A, we wouldn't add this number to A. We'd use this number to look something up in memory. We'd read the value from memory, and we would add that data from memory into our register A, for instance. Okay. So is there something they're not saying about the address mode specifier? Yes, there are a number of different addressing modes that we're not covering right now, other than immediate and direct mode. So here are some sample instructions and the corresponding opcode. And if you're feeling up to it, you can try to figure out what these opcodes are in hex. The first one is an instruction to stop execution. So it's 4 bits and they're all zeros. Not surprisingly, that's a hex 0. In our PEP8 machine, initially memory is filled with all zeros, which means that your program won't do anything. It just stops. Here we have a pattern which says load the operand into the A register. So these would be the first 4 bits, and you have that 16-bit word that follows that might go into the register A. If you can figure out what this is in hex, you've got this leftmost digit so we've got a 1, 2, 4, and 8. So this is 8 plus 4 is 12. 9, A, B. So that would be a B, I think. Right? So you can translate from these binary codes to hexadecimal digits. 4 bits is a single hex digit, so that's convenient. Here we have character input. This would be 4, and character output, that would be a 5. Okay. And these are 5-bit opcodes because they don't deal with registers. Character input and output only goes to memory. Here we have some sample instructions, and you can try to figure out what the hexadecimal would be and also what they mean. So you have to go back a few slides or pull your book out and look them up. So here we have in hexadecimal that 4-bit corresponds to 12 in decimal, which would be A, B, C, I think. Is that right? I can't ever deal with hex, so 9 is 1, 0, 0, 1. A is 1, 0, 1, 0. B is 1, 0, 1, 1. And C is 1, 1, 0, 0. D is 1, 1, 0, 1. E is 1, 1, 1, 0. And F is 1, 1, 1, 1. So that set of, I have to kind of have like a little lookup table that I'll create. And it's easy to count in binary and figure out what the hex is. So here we've got in hex, this is C0. So instruction C0, if we go and we look up that binary pattern, I'm going to jump back a slide, load operand into the A register. So this is going to load into the A register. I'm writing LDA as sort of a mnemonic to help me understand what this C0 hexadecimal instruction means. So what is it going to do? It's going to, in the A register, it's going to store, this is 1, 2, 4. So it's going to store 4 plus 2 plus 1 is 7. So this is basically saying A is getting 7 in immediate mode. Right? So I'm going to write I to indicate that that's in immediate mode. Right, so the full instruction, yeah. So here we have another one. This is again C, and then this other hexadecimal digit is a 1. That's also loading into the A register, and it's going to load whatever is in this memory address. It's using direct mode instead of immediate mode. So this means direct. And this address is 1F. Right? So it's going to go to address 1F and read that into register A. So we can see here that this sequence of bits that gets fed into the CPU, we can think of that more concisely as the hexadecimal number C1, but also as kind of this mnemonic. I'm going to load into register A using direct mode. What am I going to load? I'm going to load 1F. These other instructions I'm going to skip over. You got your book. You can try to figure out what they are in hex. So this would be E0 and this would be E1, whatever that is. And I'll leave that to you to go look up. But this is going to be some mnemonic using direct address and some mnemonic using immediate mode addressing. Yeah. So I believe that these ones, this one for instance, I believe is character input, but you'll have to look that up, character input. So this would be reading from memory address A and storing it into a, I'm sorry, this would be reading from a keyboard, and it would store it, it would read a key and store it into address A in memory. And these are character output, so this must be character output. So this would be immediate mode. So whatever character you put here, this would be the ASCII, and if you don't know what ASCII is, you're going to need to Google it. Basically, every single letter has a corresponding number that goes with it, and this is the ASCII character 41, which is probably like an A or a B. It's going to output that character, whatever that is, to the screen. So here we can kind of see a little bit of how we would do the Hello World program. So this is the ASCII, this is the 50, which, by the way, this is 51, and this is 50. So that's character output with immediate mode. All right. So this is 50 character output, and it's going to output this, which is the ASCII character code for H. And we're doing that same instruction multiple times in a row to output H, E, L, L. See, it's the same thing twice, and O. So this program is just designed to, one after the other, write H, E, L, L, O. It's a pretty typical example of a first program. It's writing the Hello World. Now you can trace through a program, these are zeros, you can trace through a program like that by writing out, what I would recommend you do is you put each instruction on its own line. So you have address 0, 1, plus 2. So your addresses start at 0 and then 3, 6, 9 going down. That's what your program counter would be as you execute the program. The first instruction is 50, 0, 0, 48. And your second instruction is 50, 0, 0, and it is 65. 6C, 6C, and 6F. The next one is going to be, so 12 in hex. So we have 9A, which is 10, B, C. So this is address C. 9, yes. And that would be 50, 0, 0, 6F. And D, E, F. So line F should be 0, 0, and then we don't care what comes after. This is your program. This is what memory will look like when it pulls the machine code into memory on your computer. And we can trace the execution. So in order to trace the execution, I'm going to put the arrow where the program counter is, and then when we advance the program counter, I'm going to show what we've got. So just by the way, I've written down here 03. Let me do this. I wrote 0369CF in hex. In binary, a 0 is that, the 3 is that, the 6 is that 1 1 0. So that's a 6. A 9 is going to be a 1 0 1. So equals 9, and a C is going to be 1. We already saw a C. 0, and F is 1 1 1 1. So you can trace through the program one line at a time and figure out what's going on. So when the program counter is 3, that means we just executed this instruction, which means that we should have over here a 5-0 in the opcode portion of the instruction register, and down here this ought to be a 48. So this is a 4 and this is an 8. Remember the corresponding cells, the last cell is an 8. So this is a 4. So this is exactly the last instruction that would have been executed. So we have just executed the first instruction. And the program counter has been incremented to address 3, so just one instruction. So here the program counter is at address 6, and we just executed 50. And what did we output? We output character 65, which would be, I believe, the E. Right? So this is how you have to trace by hand machine code. It's not that easy to do. You have to be pretty good at converting between binary and hex. But let's wrap things up. There is a thing called a PEP8 simulator. It behaves like it's a virtual machine. In order to run a program on the PEP8 simulator, I've got a different video that does that. PEP8 is really designed for us to write in assembly, and we'll get there, but we're starting off using object code. Object code is just another way of saying machine code, or a program written in the machine's language. Right? And this is what we're going to do first. We're going to start with the machine code so that we can appreciate assembly. Now I will pull up the PEP8 virtual machine in another video, and I'll enter this program and we'll run it. But what I want you to notice is this is our program. This sequence of 3 hex digits, that is output a character, which is the uppercase H, using immediate mode, right? And then this pattern, by the way, of course, that also corresponds to the pattern of bits 0, 1, 0, 1, 0, 0, 0, 0 for the 50, and then 0, 0, 0, 0, 0, 0, 0, 0. So you can actually work it out, right? That's 2 hex zeros there, and the next hex character is going to be a 4, and the next hex character is going to be an 8. So that is the sequence of bits that goes to the CPU for that instruction. There's different ways to interpret it. This is the mnemonic way. Output a character H using immediate mode. It's immediate mode because these are zeros, as all of this binary. E, L, L, O, and stop. So that's our program. It writes out hello. The Z's just indicate the end of input. They are not part of the actual program. So I'm going to skip these slides because they don't apply, and I will show you in another video what happens in the PEP8 simulator. And we'll also, I think we'll run this program as well to see what it does.